All right, so let's do an application of some of the stuff that we were doing earlier. So, just a quick review here. On delta G, you can calculate at 298. This temperature is going to equal 298. And so under standard conditions, we could do this. Now, if temperature is equal to 298. Under standard conditions, we could figure out the delta G at any other temperature as long as we make the assumption that it's about equal to delta, well, actually, it would be delta H, temperature T, minus T delta S at that temperature T, under standard conditions, which is about equal to delta H at temperature 298 minus T delta S at 298. And so we can calculate our delta G values at 298, and we can calculate them at other temperatures other than 298. Also, you know, we could try to shift this. You know, some delta G's will vary so much with temperature that the driving force will reverse. And so we can see the point of reversal. Let's say it's non-spontaneous. We want to make it spontaneous. The point of reversal is when delta G is equal to 0. And so we could just set it to equal to 0 to see at what temperature the sign changes or what temperature the driving force does reverse. Not all reactions we could do that, but we can try it. Nonetheless, by changing the temperature, it'll make it more or less spontaneous. Even though we might not be able to completely reverse the driving force, we can still make it more or less spontaneous by adjusting the temperature. All right, this is going to equal from, you know, our relationship. We can derive this from the non-standard conditions, but maybe not necessary. Minus RT ln Q. Minus RT ln Q. Now delta G is equal to 0. Well, delta G is equal to 0. And then Q is equal to K. And this delta G could be standard or non-standard. So I'll leave that on. I'll just put standard. Now, if we're under non-standard conditions, and we have this equation, you know, delta G under non-standard conditions is equal to delta G under standard conditions plus RT ln of Q. And so this gives us different ways we can adjust the driving force. You know, temperature is one, and Q is another. This has to be at temperature T. And so typically we use this in two ways. We do this at 298 and not at 298. So we have to be careful. This is delta G at 298 is equal to delta G naught at 298. Plus RT. T is going to be 298 Kelvin. Ln of Q. Okay. If the temperature is not at 298, then this is delta G at temperature T, which is equal to delta G naught temperature T plus RT on Q. Now the same thing holds here. Delta G is equal to 0, then Q is equal to K. So we just plug that in, set this equal to 0 here. If delta G is equal to 0, then Q is equal to K, and we get this whole thing is equal to 0, which means delta G naught is equal to minus RT on the Q. And so this would be at any temperature here. Actually, it should make that delta G naught. You know, when we do this, Q goes to K because here we substitute this equal to 0, and then Q goes to K, and then delta G naught at 298 is equal to minus RT on K. And same thing here. Q is going to be K. And so looking at the strategies, one, we change the temperature or we change Q. Q depends on two things. Q depends on the concentration of the pressure, so we can manipulate the concentrations and pressures to give us a desired delta G.
This is only for reactions at equilibrium, right? And delta G not equals minus RTL and Q. Or is that always?
No, I mean, that's for any reaction. That's just going to tell you when it reaches equilibrium, that's what's going to happen. It doesn't have to start off at equilibrium. It's going to tell you, for example, K, we might not be at K. That's why we have another one, Q and K. Q is just what you're given. Let's say Q is some number, but K, from the earlier examples, K is equal to 1.486. Well, you can start off from anywhere. You don't have to start off at 1.486. In other words, you don't have to start off at equilibrium. We just know where it's going to be once it reaches equilibrium. And so, for example, one of the problems earlier that we did had a Q of 1.00. If the Q is at 1.00, are we at equilibrium? No. What's going to happen is we're going to have forward reaction or reverse reaction occur. We've got to have forward reaction occur because it has to grow bigger. In order to grow bigger, we need more product than reactant. And so we want more products. Now, Q is bigger. Let's say Q is like 1,000. If the Q is 1,000, we're not at equilibrium, but we need to have reverse reaction take place. Otherwise, it's too big. And so, we don't have to be at equilibrium. Q is just where we are currently. If Q is equal to K, then we're at equilibrium. We don't have to do anything. It's already at equilibrium. If Q is less than K, then we need forward reaction. This is equilibrium. To reach equilibrium, if Q is greater than K, then we need reverse reaction. And so forward reaction occurs, reverse reaction occurs under these circumstances because eventually we want to end up at K, correct? And K is just the number that you calculate from the equations. Now, it's the number that you calculate from the equation. So normally we get K at 298 Kelvin because that's where our data is at, 298 Kelvin. But we don't, what if we want a K at 1,000 Kelvin? Do we have a data table, appendix, let's see, that was appendix D. Do we have an appendix E with data at 1,000 Kelvin? No, we don't. And so if we want a K at a different temperature, we need data at that temperature, right? But we don't necessarily have data at that temperature. But with thermodynamics, we can kind of figure it out because let's take a look at one application of this. Application.
Do you not erase the stuff to the right?
Yeah, I'm going to leave that there. The one application we're looking at is, okay, oftentimes what we want is we want a delta G equal to 0, right? And we look for a temperature or a Q that would give us a delta G of 0, right? Temperature or Q. But another thing that we could be after is a K, like a specific K value. So for example, let's say the equilibrium just shows a very, very, very little product, but let's say we want to increase that. Well, we can increase that by changing certain conditions. That is, we can alter K by manipulating the temperature. And so let's take a look at K and temperature just quickly here. And I started this last time. So for example, if we're looking at K and temperature, we can do this under standard conditions or non-standard conditions. Let's just do this under standard conditions first. If we're looking at K in temperature, then we see that delta G naught is equal to RT ln K. If delta G naught is equal to RT ln K, then let's say I want a specific K value. From the previous reaction, the K was 1.486, meaning that at 1.486, it's close to 1-to-1 product to reactant ratio, right, once we hit equilibrium. But do you know we could change the extent of the reaction by manipulating the temperature? So for example, let's say I want more reactant to form. You know, I don't want to stop here. I just want more product. I mean, not more reactant. I want more product to form. I want more reactant to react. And so here, let's say I don't want that. I want more. And so if I want more product, can I get more product? Well, it looks like I'm stuck. I'm stuck at a 1.5 to 1 ratio, because this is a ratio of product to reactant, right? This is about 1.5 to 1. But let's say I don't want that. Let's say I want more. Is it feasible to get more from this? Because I don't want to be stuck at 1.486. And so that type of problem, we could try, you know, to solve in different ways. You know, let's say I just want a little bit more product. Let's say maybe I want a K. Let's say we want a K a little higher, just a little bit more product. Let's go with a K of 104. You know, if I get a K of 104, that's a little better in terms of product to reactant ratio. Is it possible to get that K? You know, or am I stuck at 1.486? This is for the copper reaction. Do you guys recall the copper reaction, which was 1.486 was the average. So can we get more? Well, we could try. How could we possibly get more? Well, K depends on temperature. Well, K depends on temperature. Maybe I could do that, you know, just figure it out. Although I don't have my delta G naught data from this one, shoot. Or my delta H, because copper, was copper 1 in the appendix D? No, it wasn't. And so this particular problem, I'm kind of stuck here with missing some data. But maybe I can. Let's say, you know, if I want to change my K, what can I do? Well, I can change my temperature maybe, and that might change my K, or will it? And so let's take a look at the problem where we do have some data with. And so this one, we're missing the data here. No data in appendix D. And so what we're going to do is we're going to go and look at a reaction in which we do have some data, like this one. Let's try this. If I go with nitrogen and hydrogen gas, reacting to form ammonia. This will be ammonia gas here. And let's figure out what the K value for this reaction is. I want the K, you know. And so I could rearrange this equation over here and then just get my K value is going to equal E to the, E to the minus delta G naught over RT. And so I've just got to figure out what delta G naught for this reaction is. Do you recognize the type of reaction this is? This is chapter 7. What kind of reaction is this? Do you immediately see it? We have a name. You know, this is just K as a reaction. This is some reaction, but we immediately have a name for this type of reaction from chapter 7. What type of reaction is that? Can you see it right away? Or not? Yeah? Covalent bond reaction? The covalent bonds are broken and formed. But no, it has to be a name from chapter 7. Well, okay, maybe it is a combination. It's addition, but that's chapter 3, chapter 4 type. I'm talking chapter 7 specifically. If you don't recognize
Exothermic, endothermic reaction.
well, this one, it could be endothermic or exothermic reaction, but that's not what I'm looking for. I'm looking for if you recognize this right away. It's not an acid base. That would be from, you know, the chemical reactions. So maybe you haven't seen enough of these. If you haven't seen enough of these, you definitely want to get some more practice with this. This reaction is, immediately when I see this reaction, it should be clear that this is a formation reaction. You know, it's actually 2 times the formation reaction of ammonia. The formation reaction is defined based on, in chapter 7, is its formation of 1 mole of substance from the elements of their standard or stable states under the conditions given. Under the condition, nitrogen would be gas, hydrogen is a gas, so this is actually 2 times the formation of ammonia, right on. And so this type of question pops up in multiple choice. If you're thinking you're gonna take some, I don't know, you probably aren't gonna take any chemistry, who knows. A question pops up like this, you know, they give you the formation data. You should be able to connect the 2, hopefully. But, you know, formation reactions took up one whole section of chapter 7. You know? And so there are only like, how many sections in chapter 7? There are only like 12 sections or something. Less than 10, I forgot. But, you know, you want to make it a point to know, you know, what is the major topic of each section, for sure. Well, that means the calculation for this is so quick. You know, so I picked this one because the calculation is easy. You know, the delta H, the delta G, and the delta S calculation. Well, actually, delta S isn't so easy. Delta S is a little bit more difficult. And so let's take a look at the data for this one. I was having this problem. Okay, so take a look at the formation values for that. I couldn't open some web pages. All right, since this is the formation of 2 moles of ammonia, we have to multiply this by 2. It will be minus 53 kilojoules. So delta G naught here is minus 53.0 kilojoules per 2 moles. I'm not going to write per mole because we're forming 2 moles of this. And so I just plug that in here. Now K, this data is only valid at 298. And so this K would be K at 298 Kelvin. And so if K at 298 Kelvin is going to equal E to the minus delta G naught. So R is in joules. So what I'm going to do is I'm just going to convert this to 53,000 joules, or 8.3145 joules per mole Kelvin. Now, this is per 2 moles, so I'm going to get rid of the moles because I'm just going to make sure the moles are balanced out. Per Kelvin times 298 Kelvin. So what does that come out to for our delta G? Oops. Oh, you're right. I did. It makes a difference in the state. I should have used gas. If I used gas, the correct one, it would be 32.90. Sorry about that. And so we're forming 2 moles of the gaseous, 32.90. And so this is going to give us 65,800 joules. So let's see what we have here. This should be a negative. Oh, but it's a negative times a negative. A negative times a negative gives us positive. Is that right? Yeah. All right, so we do this, and what do we get? 65,800 divided by 8.3145 divided by 298. What's that? Raise E to this. K is 3.41 times 10 to the 11. Is that right? Does that look right? Okay, 3.41 times 10 to 11. 3.41 times 10 to 11 is quite huge already. Barring any errors, let's see. Did I make any errors? Negative, positive. Uh-huh.
Why is it 65,000 joules?
Oh, why is this here?
No, why is that 65?
Well, this is a formation reaction. So delta G of formation for ammonia is 32,000 or 16,450 joules per mole, or 16.45 kilojoules. You see that? For there. And so if I have 2 moles of methane, I got to form 2 of that, so I just doubled this. Unless I made a mistake doubling that. I did make a mistake doubling it, didn't I? Because I doubled it twice, because it's 32,900. 32,900
So when you wrote the delta G naught, it was already doubled.
It was already doubled.
Mm.
I wrote the delta G naught because I wrote the delta G naught not per mole, I wrote it per 2 moles. But I was just mistaken because I was thinking this is formation, because I know the definition of formation. The definition of formation is per 1 mole. And so if I had two moles, it was going to be twice as much energy, so I automatically doubled it. But I doubled it and then I doubled it again, which is wrong. And so this is wrong. It's not 65,800. It should be, since I doubled it here, and that's my delta G, this should be 32,900 joules.
What's the number below 32,000? This is 8.3.
It's just R, 8.3145 joules per mole Kelvin. And so my number is wrong here. Let me redo this calculation. 32,900. 32,900 divided by 8.3145 divided by 298.
5.84 times 10 to the 5th.
5.84
84
times 10 to the 5th.
Yes, sir.
5.84 times 10 to the 5th. Okay, thanks. All right. Well, this is at 298 Kelvin. Now, when we look at this reaction, we've got N2 plus 3H2s. We're going to go to 2 NH3s here. Yes. These are all gases. I'm going to be careful with the states as well. Let's start off. Let's say I have 1.0, and you know this is what we call a. Is that a Kp or Kc or Keq? Is this a K? This K value here, is it a Kc, a Kp, or a Keq? It's a Keq. When we get these from thermodynamics, the equation of thermodynamics, this is equal to Keq. What is Keq equal to for this reaction? Keq is equal to the activity of ammonia squared divided by the activity of nitrogen divided by the activity of hydrogen cubed. The activities, you know, are, if I have a gas, the activity is going to be very close to its normal partial pressure. If I have a solution, the activity is very close to its molar concentration. And so in this case, what we say is that Keq is equal to Kp. And here, for this particular reaction, if I look at delta N of gas, I don't know if you had a chance to review anything from last week, have you? If I look at delta N of gas is the moles of gas, the products summed up minus the moles of the gas, the reactants. So it's going to be 2 minus 4. 2 minus 4 is minus 2. So we lose 2 moles of gas in undergoing the forward reaction. And so delta N of gas is minus 2. If delta N of gas is minus 2, that means Kp and Kc are not equal. And since this is a Kp, it'll be just easier just to use atmospheres. So I'm going to start off with 1.0 atmospheres here. I'm going to start off with 1.0 atmospheres here and 0 atmospheres here. And I'm just going to do this because we know what the K value for this reaction is. The K value is 5.84 times 10 to the 5th. And so, well, how much reaction is that? So what I'm going to do here is I'm going to go minus X atmospheres for the nitrogen, and then the hydrogen should be minus X atmospheres, and then the ammonia should be plus X atmospheres. And then continue on from there. How does that look so far? Does that look good? Unfortunately, I made another mistake. You see the mistake I made? This is a very common mistake. Lots of people make this mistake all the time. This mistake happened. Do you see it?
Did you take into account the number of moles?
Yeah, I didn't take into account the number of moles of the coefficient. Right, it's just a minus x plus. I should have said what?
Minus x minus 3x minus plus 2x.
Yes, right, exactly. Minus x minus 3x and plus 2x because it's a 1:3:2 ratio. I got to keep the atoms balanced because I don't want to create or destroy atoms. All the atoms still have to be there, so they have to react in this ratio. Even if it's partial reaction, stoichiometry tells us they have to react in this ratio, otherwise nothing's going to balance. And so I know I'm not going to have complete reaction, because I got a ratio. Although it looks like I have plenty of reaction. I got lots of reaction here because the amount of reaction I got here is like 100,000 to 1 or 500,000 to 1 or something, and so it seems pretty good, but we'll go. It's not huge, my earlier calculation, it was huge, 10 to 11 is pretty big. But we got to figure out how much reaction we're going to have here. So this is going to be 1.0 minus x atmosphere, 1.0 minus 3x atmospheres, and 2x atmospheres. But I got to figure out what x is. If I can figure out what x is, then I can figure out how much reaction and what my equilibrium conditions or here. Where's this? And I can because I know that this K that I just calculated, the KE cubed is equal to KP. And the KP is just going to equal the partial pressure of ammonia at equilibrium. Partial pressure of NH3 at equilibrium squared over the partial pressure of nitrogen at equilibrium times the partial pressure of hydrogen at equilibrium cubed. All right, so let's go ahead and plug in the equilibrium pressures. For ammonia, it's 2x. It's going to be 2x squared, right? And then for nitrogen, it's going to be 1.0 minus x. And then for hydrogen, it's going to be 1.0 minus 3x cubed. Does that look good? Uh-huh. Yeah, this is a very, very common error. Again, it's actually the pressure of ammonia at equilibrium is 2x. And I have to take that pressure, 2x, and square it. But I forgot to square the coefficient. This should not be 2x squared. It should be 4x squared, because I got to square everything in there. And so that's another very common error.
Why do you have to square?
Because the pressure of the ammonia is 2x. And so if I look at the pressure of the ammonia, and then I got to put that in here. The pressure of the ammonia is 2x, and then I need to square the pressure of the ammonia. Well, if I got to square the pressure of the ammonia, I got to square everything inside there. I'm sorry?
That's how it goes by itself.
Yeah. By this here, the equilibrium. Another common error is that people will get it right there. They'll do minus 3x, but when it comes to this, they always do 1 minus x for some reason. They forget the 3. It's a very common error. People do this all the time. I've seen it so many times that for some reason. Well, now we're going to just solve for x. Unfortunately, the Casio FX115 doesn't have enough power for this one because this is a fourth order polynomial equation, and a fourth order are tough to solve. No, maybe we could square root it twice. What do you think? Is this fourth order? Can we square root it? No.
There's 4 solutions.
Sometimes we could just take the square root of the whole thing, make it easier, square root both sides. But we can't in this case. That's something we look for. We look for algebraic ways of simplifying this. 5.84 times 10 to the 5th. Other people will try to graph it, but that takes too much time. You don't have time to graph this. So what do you want to do? What do you think would be the least time-consuming strategy to solve this fourth order algebraic expansion?
Successive estimation or just what?
Yeah, method of successive approximation is probably the easiest way of doing it. Well, we got to come up with a guess, we're going to come up with some kind of guess. I don't bother multiplying out the binomials. I just leave those. It's just easier to leave them as is. For successive approximations, I never set it equal to 0. It always has to be equal to some number like this. Because how do you converge to 0? 0 is infinitely small, so you'd be going on forever. And so you never set the successive approximations equal to 0 because you'll never converge on 0. When you hit 1 times 10 to the minus 100th, 1 times 10 to the minus 1,000, you're still nowhere near 0. You got to get to 1 times 10 to the minus infinity. Oh, then I just converge on 0. But anyway, let's just do this here. Tell me your first guess. Well, first you look at this number. This number tells you it's how much product versus reactant. I'm gonna, in chapter 15, I'm gonna show you an easy way to come up with the first guess. Very easy way to come up with the first guess. But before we get there, I want you to just give me a ballpark number for a first guess. What do you say? We lose.
I would say
Most of it, huh? Don't you? Wouldn't you say we lose most of it? The reactant.
I would just take the square root of 5.84, start from there.
Or what does that come out to?
2.42.
2.42 times 10 to the.
Oh shoot, I didn't account for that. I'm sorry. It actually comes out to 7.64 to 10 to the second.
Okay, 7.64 times 10 to the second would be 764. If that's our first guess, we have to go back here and say, is that a physically meaningful number? And so if we have 1 minus 764, that gives me negative 763. Can you make a pressure of negative 763? Do you guys remember from chapter 6, we have two pressures that we measure. We measure absolute pressure and we measure gauge pressure. And absolute pressure is, like, for example, in PSI, it would be PSI A. Gauge pressure is PSI G. Do you guys remember these? We're talking about absolute pressure here. With gauge pressure, there's negative pressures because, 0 is set to atmospheric pressure. So we can have a vacuum. Vacuums are measured as negative. In gauge pressures, negative pressures are possible, but in absolute, it's not. And these are absolute pressures. And so there's no way to get negative 764 atmospheres. And, even in gauge pressure, there would be no way, because usually gauges are calibrated in 0, or they're referenced to whatever atmospheric pressure is that day. So that's impossible for a first guess, unfortunately. Let's try to come up with some other guess. Tell me your first guess for this. Well,
Maybe a number less than 1.
Yeah, it should be a number less than 1, but you have to be careful because what is the limiting reagent? Can you look at this and just tell me what the limiting reagent is? No. Did you say nitrogen or hydrogen? I thought I heard nitrogen, but nitrogen is not the limiting reagent.
So it's hydrogen.
Hydrogen is the limiting reagent. If you have 1 nitrogen, you need 3 hydrogens. Do we have 3 hydrogens? No, so yeah, hydrogens are limiting reagent. We cannot have it anywhere near 1. If this is near 1, that's, you know, -3. 1 minus 3 gives us -2. Again, absolute pressure can't go negative. The lowest absolute pressure we can have is 0, which means there's no collisions, no force.
It have to be less than 0.33.
Yes. It has to be less than 0.33, so our guess has to be between 0 and 0.33. And so what do you want to guess?
0.25.
Okay, but you know, I look at the extent of the reaction. The extent of the reaction is pretty high. And so 0.25 might be, you know, 0.25, what would the percent reaction there be? You know, let's say if all 0.25 react, so if this is 0.25, then 3 times 0.25 would be 0.75. That gives us quarter of this. And so it's about, in other words, it's about 75% reaction. Are we going to get this kind of ratio with 75% reaction? This is 10 to the 5th to 1. Are we going to get that kind of ratio? No, I think it's got to be higher probably. Like, I would probably start at 0.2.
2.8, 2.9.
I'd start with 0.29. Wouldn't you say? Uh-huh.
How do you know it has to be less than 0.33?
How do I know it has to be less than 0.3? Because these numbers cannot go negative. We cannot have negative numbers in the equilibrium because, like for example, I want -1 atmosphere of hydrogen. Well, in order to get -1 atmosphere, you might have to weigh out -2 grams of hydrogen. Can you weigh out -2 grams of hydrogen? If somebody asks you, okay, go out and weigh -10 grams of sodium chloride, salt, table salt, you say, what are you talking about? -10 grams? What is that? Maybe it's antimatter or something. I don't know. Anyway, I'd like to pass out -$10 bills. If I pass everybody out a -$10 bill, then there's no such thing as -10. That means you have to give me a positive $10 bill back, right? Something like that. Anyway, going back to this here, we'll just take a guess. I mean, we could have guessed 0.25. That's fine. And so we'll guess X here, and then we'll check our K here. And so I think it's kind of high, 0.29. I think it's going to be 0.299 something. I mean, I think they're going to be more than 1.9 following that too, but we'll see. And so I'll use my calculator here. Usually I'd like to start off with 1 sig fig for my guess. I don't like to get too precise, but if I start off with 1 sig fig, I know it's going to be way off, but 0.2 is going to be way off. Because of the ratio. So I'm going to go 0.29 squared. Or actually, should I do the denominator first? I'm going to do the denominator first. I'm going to go 3 times 0.29 equals negative plus 1 equals cube that times 1 minus 0.29 would be 0.71. So times 0.71 equals, invert this, times 4 times 0.29 cubed. 2.43 times 10 to the minus 2. You know, this calculator, I can't tell if I hit the button or not because it doesn't show me. I gotta put a better calculator on my phone because I'm not sure if I hit equals or not. Is that what other people got? I should grab my other calculator. See what I'm doing. But I'll have you check my answer. You know, you should always double check your answer. I would do it, but in an effort to save time, I'd like you to check my answer for me.
I got 215.6.
You got 215.6? 215.6? Okay, thank you. If more people got 215.6, I think I blew it. 215.6. This is usually how science checks itself, you know, because oftentimes you can't look in the answer book. You know, if you're a practicing scientist, you know, you're given a problem, and you go, wait, okay, I just got to check the answer book, you know, the solutions manual. And I'll tell you, nobody's going to pay you anything to repeat something that has the answer in the solutions manual. Right? And so you're going to come up with something, and then we got to figure out if it's a reasonable answer. A lot of people, you know, will want to ask somebody, "Is this right?" But oftentimes you run out of people to ask, and there's no solution. Figure it out yourself. 215.6. So we're too small, right? We got to go bigger. And so the way I'm going to go bigger is I'm going to go 0.299. Add another 9 on there. Well, that's going to give us more. You know, we started off with. So let me try this calculator. Or actually, I'm going to go get my other. I don't like solving the quadratic by hand, so that's why I like calculators like the Casio. They'll solve the quadratic for me. But I lost it, and so I have this. This calculator is a $1.99 calculator, 99 cents, which is okay. But the only drawback is it won't do the quadratic. But it has a line. Does somebody have it already?
466.8.
466. Wow. We're still really far off, aren't we? We're 10 squared. We got to go to 10 to the fifth. 466.8. I'm going to go big.
1.2.
We can't go 0.3 too because it'll throw us into negative here.
No, it's wrong. It's 0.33, that's the max. 0.33.
Oh, you're right. You're right. 0.32. Great. 0.33 is the max, right? 0.3, what should we do? 3.3? 3.2? All right, let's try 3.2. Let's see what that gives us. All right, let's see. Oh, did you get it already? Oh, that's good. What did you get? 9411.76. So this is 10 to the 4th. Oh, this is very close. We've got to go 10 to the 5th. So what do you want to guess here?
Packets 15563.
15563.4.
0.4. Yeah, that's 0.322.
0.322. So that's still 10 to the 4th, right? 1, 2, 3, 4, 10 to the 4th. We've got to go 10 to the 5th. I mean, this is better. This is 10 to the 3rd, so 10 to the... Should we try?
.3299.
3299? All right. What did you get?
Well, actually, I just did .329, but that was 2.9 times 10 to the 5th.
2.9 times 10 to the 5th?
Yeah.
All right. So I'll write that in here just for reference. 0.329 gave you 2.9 times 10 to the 5th. So that's very close. And so what did you do next? 0.329. 9, you said?
Probably, yeah.
All right. We could try that.
Could we do 0.33?
We could do 0.33 also.
That's 650,149.
All right. Let's try 0.33. Usually I try to stay, I would go 0.32 to 0.33. That's what I would have done, because then I would border it to 2 digits, and then I'd start narrowing it to the 3rd digit. So that's not my normal strategy.
0.33 is 650.
650.
149.
149.
0.2.
1, 2, 3, 4, 5. Okay, so this would give us 6.5 times 10 to the 5th. Oh, it's very close. Okay, then I'd go, this is what I would do. I'd look at 32 and 33 and then go like this. I'd look, okay, at 32 we have about 1, times 10 to the 5th. This would be close to 1 times 10 to the 5th. And over here we have, let's say, 6.5 or 7. Let's go with 7. And so we go from 1 to 7. 1 to 7. But we're at about 6.
So if you do 0.3299, that would be 5.9, 10 to the 5th.
3299 would be 5 point what? 9?
5.9 and then 10 to the 5th.
Okay, give me one more digit.
94.
5.94 times 10 to the 5th?
Yeah.
We want one more digit so we can try to help
Yeah.
narrow it down more precisely. And so this is a little bit too big. And so what I would try next would be something like 0.3298, and then see, and then narrow it down between these two, 3.298 and 3.299.
Then 5.45 10 to the
5.45 times 10 to the fifth.
yeah.
All right, so 545 to 594, and we want 584. And so this is about 5 units here. We want to go 1 unit down. So 1 out of fifth would be about 20% below this. So I would probably do like 0.32988 is probably what I would do next. But, you know, you could do whatever you want.
That's 5.842.
5.842 times 10 to the fifth. Okay, then we're good because this would round to 5.84. We have a lot of digits here, and you go, wow, do we need, because when you look at the sig figs here, we aren't allowed that many digits. But the problem is, you know, there's a lot of reaction that occurs here, so we don't want any round off error as possible, so this is why I carry it. But, and try to do it on here. And so, okay. Now, this pressure here is going to be 1.0 minus what we just calculated for X, 0.32988. 0.32988. And so this gives us 0.10. 2, 1, 0, 7, 6. I carry some extra digits because I'm going to double check this and I don't want any round off error. Yeah. All right. The hydrogen is going to be 1.0 minus 3 times 0.32988. 988. 3 times 0.32988. 0.98964. 0.98964. And so this is 6, 3, 0, 1, 0. Right, and then 2 is equal to 0.98964. All right, now, you know, what I'd like to do is I'd just like to check it in the solutions manual, but we don't have any solutions manual for this problem because I just made this problem up. You can't check your answer in the solutions guide. How are you going to check your answer? Is there a way we could check the answer? Well, one way we could check our answers, double check our answers, just to make sure, you know, the equilibrium partial pressures here should give us this ratio, 5.84. I mean, this is a little bit circular, but what it does is it just sees if you made some kind of simple algebra mistake, or subtraction or addition mistake. And so what we'll do is, for a double check, we always do this in equilibrium calculation like this. This is Chem 1B stoichiometry, which we call equilibrium. The double check is these equilibrium concentrations have to be in this ratio, you know, that equals 5.84 times 10 to the fifth. And so we'll just plug in the ammonia concentration in equilibrium. The ammonia concentration in equilibrium is 0.98964. Now, the units here we leave off. We omit the units because in reality, this is a KEQ, and KEQs are dimensionless. They don't have units. And so we're just saying that, you know, the partial pressure is close to the pressure in bars. Ah, shoot, this should be the pressure in bars. not the pressure in atmosphere. But it's okay, let's leave it. And, do I have to multiply this by 2? Do I have to multiply this by 2? Isn't there a 2x there? Or did I already multiply it? If I multiplied this again by 2, would I be doubling and then doubling again? Is that,
You're supposed to do that. You're supposed to,
or in other words, should it be 0.98964 or should it be 2 times 0.98964?
I think the
No.
number is wrong. Because if you multiply
That's
two,
That's the times 3 one, from the second one.
Oh, is it the times 3? Did I screw that up?
yeah, if 2 times 0.988 is 0.659.
Oh, okay, I screwed that up. Then, you know what? Why did I do times 3? Oh, this is why I did times 3. This is actually times 2. And I just used this, which was wrong.
Yeah, this is 0.6597.
0.6597?
76.
6?
Yeah.
Okay. The other thing I made a mistake with is this. The data I got for delta G was from Appendix D. And Appendix D is not in atmospheres. Appendix D is in...
bars.
Yeah.
Oh.
So let's just cancel out on the bottom. Sorry. All these units should be
Bars.
bars, not atmospheres.
So they're also
Hmm?
up in the equation also.
Yep, in the equation also. You know, I'm just going to cross it down. We'll just cross it down. All bars.
That doesn't change our number, does it?
No, the numbers are the same.
Okay,
It's
thank
just-
goodness.
Just the units are wrong. Appendix D. I have to watch out because now, you know, we got the data tables in atmosphere and we got data table in bars. So I have to be especially careful. Although, you know, the number is going to come out very close. Very close because, you know,
They're practically 1-to-1.
they're practically 1-to-1. It's 1.01 bars to an atmosphere, so it's very close. All right, so let's do our double check here. All right, I need to plug in the concentration of ammonia. Now the concentration of ammonia says 2 times that. So should I double this pressure here? No, the answer is no because, you know, you already doubled it. Doubled it, you know, it's 0.32988. That would be doubling it twice, which is wrong. And so this is just 0.65976. You know, it's the pressure that we calculated. Then this is squared. The confusion arises because a lot of people will see this. It's 2x quantity squared, and they'll think that x is the concentration. X is not the concentration. X is the number we got from algebra. The concentration is 2x, which is this number here. So we already doubled that x value to get that. And so this is going to be the nitrogen, which is going to be 0.67012. And then the hydrogen is going to be 0.01036. Again, the reason I carry a lot of extra digits is because of the double check. If I round this off, if you were to round those to the proper number of 6 pigs, you know, your number is going to be way off. We round off error. Well, maybe our number is still going to be way off, but if it's way off, then I know I made a calculation error or some other error, not round off error. And so what does it come out to? It's 65976 squared. Yeah, 584. 584.1. Oh no, that's a comma, sorry. 584,000. 584,171. 2, 3, 4, 5. Okay. 5.84 times 10 to the 5th. It's good. Okay, so we're good. So double check is good. Now, when we look at this, you know, what was the percent reaction here? Now, how much of the reactants reacted? Now, the percent reaction is going to be based on the limiting reagent. We figured out, what was the limiting reagent again? The percent reaction, was the limiting reagent the nitrogen or the hydrogen? The nitrogen? Nitrogen was the limiting reagent? Or hydrogen? All right, so we want to figure out the percent reagent, percent reaction. The percent reaction is going to equal, you know, how much was lost. How much was lost is 3x over how much did we have initial. And so what it is it's going to be the change, you know, the loss over the initial times 100%. And so here, the change is 3x. The initial is 1.0. And so 3x is, so in other words, it's 0.98964 over 1.0 times 100. And it's going to be 98.9. Actually, we aren't allowed that many digits, so it's like 98.9%, 99% reaction, 98.96. We're actually only allowed 2 sig figs. Let me subscript both of those. So 98.96, 99% reaction. You know, I would like to shoot. I'm going to shoot. I want 99.9% reaction. I don't want this 98.96%. I want 99.9. Possible? Possible to get 99.9% reaction out of this? In fact, it's going to be very difficult to get 100%, but let's go for, or maybe I want less. You know, maybe I don't want as much. What do you want? More reaction or less reaction to this? Well, you might say, oh, I'm happy. You know, this is 98.9%. This 99% reaction is good enough for me. But let's go for a little more. And so in this next example, we're going to set a target. You know, this target is we're going to go for 99.99% reaction. We're going to go for 99.99% reaction. Okay. We want 99.99. Is it possible? You know, and if so, how do we do it? And so let's just go back to our reaction here. Is N2 equals 3H2 yields 2 NH3s. And we recall that our limiting reagent is, and this time I'll do it right. This is 1.0 bars. This is 1.0 bars. Our limiting reagent is going to be 0 bars. Is the hydrogen. And so if I lose 99.99%, I'm going to run out of sig figs, so I'm going to carry extra. I'm going to lose 0.9999 bars worth. You know, if I call that 100, you know, just add another 0 in there. And so I'm going to be left over with, this would be my change, I should be left over with 0.0001 bar remaining. This, okay. So if I lose that much hydrogen, how much nitrogen did I lose? The same is incorrect. The same, because the nitrogen is the excess reagent. And so, it being the excess reagent, we should lose a smaller percentage.
Use exactly what it
1/3?
Yeah, the nitrogen.
Well, we want it to be a little bit more, because 1/3 would introduce some round off, a little bit of round off there. How would I calculate a more precise number than 1/3? 1/3 is very close, you're right.
0.999 over 3. 1 minus
Yeah.
0.999.
Okay, what we do is, yeah, we look at this. We call this, I don't necessarily, when I kind of know the number, I call it a y rather than an x, because I know what the number is. And so I'm going to call this number, this is the same thing as minus 3x. And therefore, this is minus x because of the coefficients. And so you're absolutely right, it would be 1/3 of this change would be this. And so what is 1/3 of 0.9999? Well, 1/3 of that would be 0.3333. So this would be, and likewise, we could figure out what this number is, because this number is going to be plus 2x. If this number is plus 2x, and x is this, then this has got to be what? 0.6666 bar. Right, so that tells us. And so what we're going to be left with here is going to be 0.6666 bar, and we'll have 0.6666 bar. And so what I want to do is I want this reaction to go and then stop here. Can I make it stop here? I can make it stop here if this is K. And so if this is K, the reaction will stop here. Well, how can I make that the K? Well, first let's figure out what K is, because this is where I want the K to stop. And so figuring out the K value here, K is going to equal the ammonia squared, so 0.6666 squared, over the nitrogen, 0.6666, over the hydrogen cubed, 0.0001 cubed. And so what does this come out to here? Actually, yeah. So 6 times 10 to 11. Is that what other people got? All right, this is what we want. If the K is equal to this, then the reaction will proceed and then stop here. And so the strategy is we have to get the K equal to this. So we need to change the K. So must change K from 5.84 times 10 to the 5th to 6.6666 times 10 to the 11th. If we can do that, then we can tailor the amount of reaction we have. And so is there a way to change K using the the equations from thermodynamics. Yeah, you know, I think we could do it like this. For example, we know that delta G naught is equal to minus RT ln of K. And then just we can change the temperature, right? So what I'll do is I'll just do it like this. We change the temperature, solve this equation for T. T is going to equal minus delta G naught over R ln of K. And then just plug it in, right? If we plug it in, what was the delta G naught value that we calculated earlier? 32.9, was it? And so that was a minus 32,900 joules divided by R, 8.3145 joules per Kelvin. ln, and just plug in the desired K value, which was the 66666 times 10 to the 11. And so let's do that and see what happens here. Okay, this is different than my natural log. I got 145.3 Kelvin. Is that what you got? Yeah. It's really cold, actually. Really cold. Ammonia is going to liquefy by that temperature, so maybe this is not a achievable temperature, but unfortunately, I didn't make a mistake, I think. You see what mistake I made? You know, it would be nice if the if there was some kind of alarm, you know, some warning alarm went off if I make a mistake like this. Do you see the mistake I made? The mistake is not so clear because I think I already fixed the mistake with the delta G. Remember doubling it and then doubling it again. So I used the right delta G, and then R, and then K. So
You didn't do the right equation for portions?
well, is that the right equation? Well, that's the equation. That's one of the equations.
No, I mean on the I, where you set, nitrogen is 1.0, then hydrogen 1.0, and do the ammonia is 0 bar.
You mean here, these original coefficients,
Yeah.
like a 1 to 3 ratio? Actually, it doesn't matter what I start off with, because oftentimes we don't. When we get it correct, like so, for example, if I did this, if I made this 3 a 1 to 3, we call it a stoichiometric reaction. But most reactions aren't stoichiometric. Most reactions are limiting reagent, excess reagent type problems. If you have limiting reagent, excess reagent, it doesn't matter how much excess. Is there a fixed amount of excess reagent you can have? It has to be twice as much, 3 times? No, you can have any amount of excess reagent you want. It's not going to react.
The units of delta G should be joule per mole.
No, well, for this one, remember I had to modify it because we're doing per 2 moles, not per 1 mole. If I look at delta G here, this is by definition this is per 1 mole of ammonia, and I got 2 moles. So the moles cancel out. I automatically did that here. I automatically did that because if I were to use that value there, it should be 16,450. 16,450 per mole. That's per 1 mole of ammonia formed. I'm not doing that. Yeah.
Delta G is for ammonia only, or like for the entire reaction?
It's for the entire reaction because I lucked out. I lucked out because I recognize it's a formation reaction. Even if I didn't luck out, it would have been easy because delta G of formation for the elements in their standard state are 0. And so it would have been delta G of formation of the products, this, minus delta G of formation of the reactants. Delta G of formation of nitrogen, 0. Delta G of formation of hydrogen, 0. But, you know, I would have saved a little bit of time not having to hassle with that. That little bit of time means extra time for other questions that you may have. Time, you know, it's the people who can do things fast, you know, end up with the top scores because they have extra time. They can work on the challenging problems. You know, people who spend a lot of time. And so, how do you get speed? You get speed through practice and familiarity and this kind of stuff. And so, a lot of people say, "Yeah, speed doesn't matter." It does matter on timed exams. It makes a big difference. You know how much you can do. And does anybody see my mistake? Unfortunately, this is what I said. Unfortunately, there's no warning that goes off saying you're about to make a terrible mistake, which I did. I made a terrible mistake.
Is that the equation?
The equation's correct. All the numbers are correct. I made a terrible mistake. Or, you know, the equation's correct.
It's not the sign?
Hmm?
What about the sign? The sign of R?
No, the sign's okay. I didn't make a sign error. Sign error, I can go back and fix that. Calculation's correct. The calculation's right, the equation looks right, but it's wrong. It's wrong because you have to memorize things in thermodynamics. It's like, you know, when I ask you about a formation reaction, you go, big deal, you know, who cares about formation reactions? But the problem with thermodynamics is, if you say big deal, you know, I got the equation, I don't really care about all the extraneous, I don't care about the definition, I don't care about the definition of formation. I can live, and I've lived, you know, many years without having to know the definition of formation reaction. But if you don't know how this equation works, then you're in big trouble. You're in big trouble because you're going to use it assuming that everything looks good, and everything does look good. You know, it looks like we did the calculation correctly, but we made a terrible mistake, a very embarrassing mistake, unfortunately. What was my very embarrassing mistake? In other words, if you were to do this in like a presentation, well, hopefully you won't, because hopefully, you know, we have peer review in science. In peer review, you just ask your friends, you ask your neighbors, you ask your lab partners, you know, does this look good? Did I make some stupid mistake here? And then hopefully they catch it, because I did. I made a bad mistake here, and the bad mistake is. See, this is the little things that you forget. The little things that you forget is, if I use delta G out of the table is in bar, you know? That's easy to forget, in bar. What else is special about that table? Yeah, it's kilojoules, so you gotta remember that. What else? The temperature. What is the temperature of the delta, the table? 298. And so what I just did here is, this is the delta G. This delta G is only valid at 298 Kelvin. That was my terrible mistake. I can't use that delta G value because we're not at 298 Kelvin, right? In fact, if this temperature was 145.3 Kelvin, I better use the delta G at that temperature. But this temperature is wrong because I used the wrong delta G, so I'm not even going to bother calculating delta G at 145 Kelvin, because it's totally wrong. And so in order to use this, I can't use this. this is correct. I mean, the algebra is right. Everything looks right, but there's no warning system here. You have to know it. In order to know it, you have to use it, and you have to practice it. And so this is the wrong equation, even though it looks like the right equation, and this equation is in the book. And this is a very common mistake. I'd say about 1/3 of the class fails on this problem because they'll just use this equation, plug in the numbers, and think they have the answer. Well, it varies. Some bad semesters, I've had more than 50% of the class screw this problem up, you know, by using the wrong delta G in there. And so I give warnings like this. Every semester I give the same warning, the same spiel, but every semester I see the same result.
So how would you find the temperature? What would be the delta G?
We need the delta G at the temperature that we're trying to solve for, and since we don't know what the temperature we're trying to solve for is, we can't figure out the delta G. It's impossible. Uh-huh.
So,
Would you use delta G non-standard conditions and then set delta G equal to 0 and solve for T?
Well, you know, if we do delta G under non-standard conditions, this is what we get. If we do delta G under non-standard conditions, delta G under non-standard conditions is delta G under standard conditions plus RT ln a Q. Now, if we set this to 0, look what happens. If we set this to 0, then Q becomes K, right? And so the first thing is we'll go delta G plus RT ln of K is equal to 0. And then we go, well, we'll just subtract minus RT ln of K from both sides, and we'll go delta G naught is equal to minus RT ln of K. And you know what? We're back to where we just started. It looks right. Everything's right. What you say is right. Problem is that delta G is going to give us trouble because we need the delta G at that temperature, and we don't even know what the temperature is. So how can we solve for the delta G at that temperature? We can't. And so you have to know the equations of thermodynamics. You have to, you know, use them and then get familiar with them. But you don't have that much time, so you have to do this quickly. So we got to figure out: is there a way we can? Is there a way we don't have to solve for delta G? Delta G changes significantly with temperature, so we've got to figure out, is there a way to do this without doing this? And then the answer is yes. This is what I ended up doing last time. You know, we don't know what delta G at temperature T is, you know? We aren't going to get that. Well, we know that delta G naught is also equal to what? Yeah. And so it's equal to delta H naught minus T delta S naught. And what we could do here is we could do this. You know, normally these are temperature T, right? But we can make an assumption. What's the assumption that we can make? Oops, is it time?
Yeah.
Oh, sorry. I just lost track of time there.